4.26. A solenoid 60 centimeter long and of radius 4 centimeter has 3 layers of windings of 300 tons each. A 2 centimeter long wire of mass 2.5 gram lies inside the solenoid near its center, normal to its axis. Both the wire and the axis of the solenoid are in the horizontal plane. The wire is connected through two leads parallel to the axis of the solenoid to an external battery, which supplies a current 6 ampere in the wire. What value of current in the windings of the solenoid can support the weight of the wire? Take G, that is 9.8 meter per second square. Now suppose this is the solenoid. See, like this. This is the axis of the solenoid. Okay. Now on the axis, a small piece of wire is placed here, just like this one. This is a piece of wire and it is placed here. Clear to all of you? This is the piece of wire inside the solenoid on the axis of it. And this one is perpendicular to the axis. Now, these two ends of the wire are connected with the battery. Battery is outside the solenoid. Then current flows through this one. Current is also flowing through the solenoid. It implies that along the axis of the solenoid, there is the magnetic field. So this particular current carrying wire is in the magnetic field of the solenoid. So on this wire, the force ILB sin theta, but this wire is perpendicular to the axis and field is along the axis, means theta is 90. So force on this wire, that is ILB. Now, if this particular force that is exactly equal to mg, then here the wire that will be balanced, or we can say it will remain suspended inside the solenoid. Now, for that, how much current should be passed through the solenoid, that is asked here. Now, question clear? Now see, length of the solenoid, that is 60 centimeters, so 0.6 meter. Radius of the solenoid given to you, but it is not important. Now, what should be the current through the solenoid that we want to calculate? 3 layers of winding, each with 300 tons in the solenoid are there. Okay. Now, length of the wire, that is 2 centimeter. So that is 2 into 10 raised to minus 2 meter. Mass of the wire, that is 2.5 gram. So that is 2.5 into 10 raised to minus 3 kilogram. Current through the wire, that is 6 ampere, and G that we have to take 9.8 meter per second square. Now see, inside the solenoid, the magnetic field produced, that is mu 0 n I. Mu 0, that is 4 pi into 10 raised to minus 7. And that is number of turns per unit length. Here see, total number of turns, that is 3 into 300. 3 layers are there, and in each layer 300 turns are there. So total number of turns, that is 3 into 300 divided by total length of the solenoid. So that will give you number of turns per unit length. Current passed through the solenoid, that we have to find. Okay, so keep I as it is. So here your answer, that will be 6 pi into 10 raised to minus 4 I. That is your B. Now, in this particular magnetic field, the current carrying wire is placed. So, to balance the weight of the wire, the magnetic force on the wire which is I dash BL, that should be equal to mg, where I dash, that is the current through that wire. So F, that is I dash LB, I dash, that is 6 ampere, length of the wire, that is 2 into 10 raised to minus 2, B, that we calculated previously, that is 6 pi into 10 raised to minus 4 into I, that should be equal to mg, where m, that is 2.5 into 10 raised to minus 3, take g, that is 9.8, and now solve this equation and make I as a subject of equation, you will get the current through the solenoid. Clear to all of you?